Hey folks, in this discussion we're going to talk about the electric field created by a plane of charge. And this stems from the previous discussion. In the previous video, we derived an equation for the electric field created by a finite disk of charge, like a pi tin or something like that. And we got this crazy expression, okay? On here, x is how far away you are from the pi tin, and r, big R, is the radius of the pi tin. So it turns out that with this equation, we can extend this to make that into an equation of an electric field created by a plane of charge. And that's really simple. Okay, what we're going to do is we're going to make x much, much smaller than r. In other words, if here's our pi tin, okay, and here's the center of our pi tin, and we are like right above the center, very close to the pi tin, then x is way, way smaller than r. And in our point of view, it looks like an almost infinite plane of charge. So we're going to make x really small, or the other way of looking at this is making r really, really big. In other words, make a really, really, really big pi tin and put yourself close to it, okay? And that's a plane of charge. So we're just going to start with the answer from the previous example and make r much, much bigger than x. So we got 2 pi k sigma, 1 minus, okay. Well, if I make r much, much bigger than x, and remember I'm adding here, so if I'm doing r plus x, the r term will dwarf the x term. So I'm going to rewrite this as x over root r squared, which is simply r. Okay, but if r is way, way bigger than x, then 1 over an x over r is going to be way, way small, like almost 0. And so you end up with the following expression. You get 2 pi k sigma, and technically times 1 minus roughly 0, which is just 1. So you get E equals 2 pi k sigma. Now remember, sigma is the surface charge density of the plane. It's like nanocoulombs per meter squared type thing. Now, we even have a shorter way to write this. K, the value in Coulomb's law, is about 9 times 10 to the ninth, and it's Newton meter squared per Coulomb squared, okay? Well, that's actually a derived constant, and here's where that's going to come into play. That constant is actually derived from a second one. K, it turns out, is equal to 1 over 4 pi times something called epsilon naught, which is I believe, the permittivity of free space. And that has a value of approximately 8.85 times 10 to the negative 12. And the units are simply the inverse of these. So it'd be Coulomb squared divided by Newton meter squared. So in place of k here, if we sub this in, the pi's drop out and the 2 over 4 becomes a half. And you get the following very easy expression for the electric field of a plane. It's equal to sigma, the surface charge density of the plane, divided by 2 times that constant epsilon naught, okay? Now, having said that, there's a peculiarity about this equation that I hope you guys have noticed. It's constant. The electric field does not vary with distance in any way. Our other examples, there was always some variation with angle or distance or something. Well, here, this is sigma and epsilon naught are both constant in this problem, so the electric field is constant. So here's why that is on a conceptual level. So here's what I want you to imagine. I want you to imagine you have a large plane of charge. I'm going to make it horizontal, okay? And what that equation is telling us is that the electric field, and I'll just draw the electric field with some representative lines here, that the electric field is constant, meaning that all the lines would be equally spaced together. Okay, so it might look something like this. If I could imagine actually seeing it, the electric field would look something like this. Okay, so that would be your electric field, and it would be constant. Now, why is that? Okay, now first of all, I'm just drawing a slice of the plane. The plane itself, it's a plane, so it'd be really big, or we're really close to it, you know. So if this is a point on the plane, let's say right here, I'm standing right above that point, very close to the plane. Well, here's the idea. basically, like if I look at that point right there, and here's the part of the plane that I'm looking at, if I imagine, okay, so everything in that cone there is going to try to make an electric field pointing up, okay? If I get far outside that cone, those fields are going to point left and right. They're going to pretty much cancel. So, for the most part, the charge that's directly below me to some extent is the only one that's going to make a significant field upward, okay? Well, imagine if I get farther away. Well, my cone gets bigger, okay? Now, you have an inverse square law. Like let's say you triple how far away you are. Well, the field should be, if it's a point charge, the electric field of a point charge is simply kq over r squared, right? How far you are away. So if I triple how far away I am, then my field should be 1/9 as large, right? But this cone, the amount of charge that's significantly contributing to the electric field is also increased. Q has also gone up. Well, how much? Well, Q equals sigma times A. Well, sigma is the density. That's not going to change. How much has your area gone up? Well, if you've tripled this distance, you've also tripled your radius of that circle. And the area of a circle is pi r squared. So it turns out that Q also goes up by 3 squared, or 9. So your r squared term goes up by 9, and your q term goes up by 9. Well, they both gone up by the same amount, so it turns out your electric field is unaffected. Okay, so that's a conceptual way of looking at why is it constant for a plane of charge. Of all the equations in this chapter that you probably should memorize, I typically don't suggest you memorize most of these answers, okay? However, this one here is one that we are going to use a lot over the next couple months. So this is one where it would probably be advisable to go ahead and memorize that. For the electric field of a plane of charge is sigma over 2 epsilon naught, and it's constant as long as you're relatively near the plane. All right, I hope that example was helpful, and thank you very much.